Okay, so the recording is in progress now. Please start.
Yeah, so let me write the title, diamond lemma, and differential graded algebras. I mean, I think that so the story I'm going to tell is a little bit different from topics that are commonly discussed in your seminar. So there is the word Lie algebras in the talk, but perhaps those Lie algebras will be not quite the Lie algebras that the seminar participants use on a daily basis. But well, let's. So it's a joint work with Pedro Tamarov. It's been on the archive about a year, I suppose, and somehow to give you some overview before giving some precise statements and technical details, I would say that there are somehow two very disjoint parts of mathematics which most people don't put in the same place, kind of. So there is the business of, let's say, homotopical algebra, homotopical algebra and deformation theory, which somehow uses the ideas proposed by Quillen in the 60s, and then developed extensively by many other people in various questions. But originally for Quillen, it was homotopical algebra was developed perhaps for purposes of algebraic topology, to understand a little bit better, for example, the rational homotopy type of a topological space and so on. But in any case, so right now these words, a lot of things have grown out of that. And then on the other side, there are things which are considered to be maybe much more down to earth. Some people maybe would say that it's something computational, things like Grobner basis and writing systems. Rewriting systems. Which at least superficially, yes, are concerned by doing computations in explicitly given algebraic objects. So, for example, you have an algebra represented by generators and relations, and you want to describe a basis or to know how to multiply basis elements. Somehow our wish for a long time has been to kind of connect these two stories, because somehow I will remind you briefly how people define and compute Grobner basis, and what somehow in many ways it's very natural to think of Grobner basis and as representing an algebra as a deformation of a much simpler algebra. And so as such, it kind of belongs to the context of deformation theory. And it would be kind of good to understand how to think about Grobner basis in that context. This was our motivation. And in some sense, we I would say, succeeded in understanding what is going on. And well, I'm going to try to explain to you how it works. So I'll start with a so I'll start with a brief reminder of Grobner basis and rewriting systems. Then equally briefly, I'll talk about some necessary background from homotopical algebra, namely I'll talk about models of algebras. And then I will connect the things together. I will somehow reinterpret what it means for a writing system to be convergent via models and via the tangent complexes. So that's roughly the plan. So let me start with the Grobner basis. I will perhaps talk about there are several different situations where people talk about Grobner basis, normal forms, writing systems. So for simplicity, let me fix the playground. I will work with possibly non-commutative associative algebras. So context, possibly non-commutative associative algebras. And those associative algebras are going to be presented by generators and relations. What does it mean to say? You have some, let's say, finite set X, which is the set of generators. Then you can define, I'll put X in these angular brackets, so some people perhaps will, in computer science, sometimes they perhaps put star, which is a little bit, well, I'm not a big fan, so I will do this. By this, I denote the free monoid generated by X. So it consists just of possible words in the alphabet X with the operation given by concatenation of words. And then you can give a field K, which is implicit here. And for the moment, there are absolutely no assumptions on the field. You can take rational numbers. You can take a field of characteristic P. You can take your favorite algebraically closed field. That absolutely doesn't matter. So you take the span, the vector space spanned by the free monoid, and this is the free associative algebra generated by X. And now I suppose you say you can choose some subset R in K of X, which will be the relations of a certain algebra, and then finally you take the quotient by the, so when I put R in the normal brackets, this is the two-sided ideal generated by R. And this quotient, you think of it as an algebra represented by generators and relations. So it has generators X and relations R. Sometimes, it's relatively easy to figure out what an algebra is. So, you know, if you take, for example, if you take X to be a two-element set, little x, little y, and you take the quotient of the free monoid by the ideal generated by xy minus yx, this is the algebra of polynomials in two variables, right? We all know and understand what this algebra is, how to multiply elements there, and so on. Things can get a little bit more involved. You can take the quotient by xy minus yx minus x. So this algebra is definitely, this quotient is definitely going to be a non-commutative algebra. In fact, well, you can somehow easily understand what this algebra is. It's the universal envelope of a certain Lie algebra, the only two-dimensional non-abelian Lie algebra up to isomorphism. Actually, let me give you two more examples of the same flavor, because it will kind of help to help my point. You can also modify the relation of commutativity a little bit and take the quotient by xy minus yx minus 1. This quotient is the first Weyl algebra, the algebra of polynomial differential operators on the line. If you think of y as multiplication by variable t and x as of derivative d over dt. And finally, in this list of examples, I want to put one more example. I take just the quotient by the ideal generated by xy. This algebra is much less interesting in a sense than the three previous ones. So the three previous ones were kind of connected to something, right? To commutative algebra, to Lie theory, to there were differential operators. And now we take this very stupid thing, just quotient by a monomial relation xy. So this is, I would say, much less interesting. But at the same time, this much less interesting algebra is quite pleasant to work with. So it's certainly, it is very easy to describe a basis, just monomials not divisible by xy. So it has a basis y to the power a x to the power b, monomial is not divisible by xy, and the product is also easy to compute. Basically, you take two monomials, you concatenate them, and the result of concatenation is either divisible by xy or not. So the product of two basis elements is either a basis element or zero. Extremely easy multiplication table. And of course, you probably know very well that in the previous three examples, monomials y to the power a, x to the power b also form a basis in each of these two algebras, but the multiplication is a little bit more complicated. Well, for polynomials, it's easy, but in the universal envelope or in the Weyl algebra, there will be some lower terms that will appear, well, because they will. What purpose do these examples serve? I want, perhaps, in the context of talking about Grobner basis, to promote a slogan. I want to say that among associative algebras that we encounter in our daily life, there are some interesting ones, and there are some algebras which are easy to work with, and the intersection of the two sets is almost empty. Among associative algebras, there are interesting ones and, well, and easy ones, and those classes are almost disjoint.
I would say that the polynomial ring is an intersection.
Yes, that's why I write almost. That's why I write almost. And Grobner bases somehow serve as one possible bridge between these two classes. A bridge between the two classes. So what does it mean precisely? Essentially, again, for the purpose of this talk, I will have a very precise meaning of the easy ones, which perhaps to follow up on Zhenya's remark, I would say the extremely easy ones, which won't include the polynomial algebra, by definition will be just algebras with monomial relations. So, as I said, if all relations that we are imposing are monomials, then we immediately see that the basis is formed by things not divisible by these monomials, and the multiplication table, the multiplication just given by concatenation and replacing things by zero if one of the relations appears. Now I want to think of other algebras as some sort of deformations of extremely easy ones. What does it mean? So suppose that we have some set of relations. Now in each relation, I want to emphasize one of the monomials, and I want to think that this is the leading monomial. Just call it a leading monomial. So in each, let's write each relation as a well, up to some scalar multiple, W minus f of W, where W is a certain monomial, a certain word in the alphabet X, and f is some linear combination of monomials. So for example, if we take the relation xy
Oh, I'm sorry.
minus,
What is lambda?
well, it's just what I mean to say. What I mean to say is that we choose some monomial which we consider important. That monomial might appear with some coefficient. So lambda is just the coefficient of that monomial.
Okay, I see. But in principle, we can
just,
ignore it, right?
Yeah. So I mean, let me just explain. I still want to look at this example. Let's take the relation xy minus yx minus x. So I can either think of this relation, I can either think that xy is the most important part, and so I think of this relation as a rule which says that xy should be replaced everywhere possible yx plus x. Or I can say that this relation is -1 times yx minus xy plus x, where now yx is the most important one, and I view my relation as a rule that replaces yx by xy minus x. So this is what I mean. So it's just lambda, yeah, it's just since at this point all monomials are on the equal footing, each given monomial might appear with some coefficient. So I take this coefficient out. Or I can do something even more weird. I can say that x is the most important guy. And I might consider the rule that replaces x by xy minus yx. So you will probably say that this third idea is a little bit stupid, because if we replace, so for example, we can start with x itself, we replace it by xy minus yx, but now new occurrences with x have arisen, so we'll have to replace it by xy minus yx times y minus y times xy minus yx, and so on and so forth. And so we keep doing that, and things just explode, and there is no end to it. So this particular choice is a little bit pointless. It does not really bring us to any place where we can say, wow, we achieved something. This just say, no, we need to do more and more and more and more and more. The first two choices are a little bit more sensible in that respect. Namely, it is relatively easy to prove that whichever element you start with, you can only apply this rewriting rule finitely many times. And after a while, everything will be rewritten as a combination of monomials of the form y to the power a, x to the power b, which in the first case, and the x to the power a, y to the power b in the second case, or in any case, these can be applied only finitely many times. So each of these can be applied finitely many times. And so in general, so a rewriting system is a collection of rewriting rules like that, rules that rewrite a monomial into a linear combination of other monomials. Monomial linear combination of monomials. Now, as we saw in the examples that I discussed, some rewriting systems are slightly better than others. Namely, a rewriting system is said to be terminating if whichever thing you started with, you can apply your rewriting rules only finitely many times. The rewriting process of every element stabilizes. Let me see. Terminating. Any element can be rewritten only only finitely many times. And somehow this is so the point of rewriting systems is that they are used to attempt to find a basis in an algebra given by generators and relations. Sometimes you might have a problem. So let me give you one more little example. So let's take three elements X, Y, and Z, and let's take the rewriting system that rewrites XY into one and rewrites YZ into one. Then you can take the element XYZ. It can be written in two different ways. You can write it as XY times Z, which can be rewritten into Z, and it's X times YZ, which can be rewritten into X. Now, as we arrive at Z at an X, we cannot rewrite things further. So we have two different results where we stop and cannot do anything else, which means that somehow if you consider an algebra, the quotient in that quotient, the coset of X is equal to the coset of Z because they both are related to X, Y, Z. But we cannot, both X and Z are, one would say, irreducible elements. They cannot be rewritten further. So somehow, but neither X nor Z can be rewritten. So somehow this motivates another bit of terminology. A rewriting system is said to be convergent if every element of every element in the free algebra actually has exactly one normal form. So terminating means that you can rewrite things, rewrite, and for every element you stop somewhere that cannot be written further. And convergent means that the place where you stopped is necessarily unique, that there are no ambiguities in how things can be. In the end, everything rewrites to the same. So every element has exactly one normal that is unwritable form. And somehow, now.
Vladimir, sorry, do you understand correctly that normal forms are those monomials not containing any of the monomial which can be rewritten?
normal forms are so unrewritable means monomials not divisible by the left-hand sides of rewriting rules.
Very good.
Exactly.
Thank you.
Right. So now, I said in the beginning that perhaps people talk more often about Grobner basis than about rewriting systems. So Grobner basis is something which is more or less the same, but under slightly stronger assumptions. So when people talk about Grobner basis, they assume that you have a total order on monomials which is multiplicative, so such that M1 is less than M2 implies M1, M3 is less than M2, M3, and M3, M1 is less than M3, M2. And then you define once you have such an order, you define a rewriting system saying that you have a choice of the monomial that you are rewriting, just the leading monomial with respect to that total order. So where the direction of rewriting is dictated by this order, by such order. But in principle, sometimes it is beneficial to consider writing systems that don't arise from total orders and order things just partially. A writing system, of course, defines a partial order. So on the other hand, each rewriting.
Sorry, can I ask a question?
Yes, of course.
But to obtain a rewriting system from a monomial order, you need not only the order but also like some set of relations, right?
Well, yes, you're right, of course. What I mean is that once you have a relation into total order, you have just one rewriting system dictated by this order. A priori, you might want to consider writing systems which don't arise in this way.
Okay, thanks.
But each rewriting system gives rise to a partial order where we say the following, that we impose conditions M1 is less than M2 if M2, if we have a rewriting rule M2 rewrites to some f of M2 and M1 appears on the right with non-zero coefficients, with non-zero coefficient. And you extend this relation, you consider transitive multiplicative closure of this. Well, multiplicative just means precisely compatibility above here. So the point is, my point is that you only, when you do rewriting, you only need to care how to order things which you in the process of rewriting. You don't need to order to compare two monomials if they never appear in when you write one thing into another. So that's.
I'm sorry. Don't we need to, for the relation to be antisymmetric, we need to require some terminate in the system?
No, but I mean, what I want to say now, what I want to say is that this partial order is defined, you can define it, but then somehow it is true that in order for things to be interesting, in order to have a chance to terminate, you require the descending chain condition. You require that there are no infinite decreasing sequences for this partial order.
No, but more simply, I mean, for it to be a partial order, you need the relation to be anti-symmetric. You do not want M1 to be less than M2 and M2 less than M1. Why doesn't it?
Yes.
Maybe I'm missing something obvious.
No. You are right. You are right. You are right. And somehow, if I write each here, yes, I should say that. Let me say that this is a comparison binary relation. Yes, thank you. No, that's you.
Okay, thanks. Yeah, I get it now.
Fair point. And then somehow, if that binary relation defined like that happens to be a partial order without infinite decreasing chains, then your writing system happens to be terminating with respect to that order, and you might ask when it is convergent. Right. So in any case,
may I ask? So M1 appears in F M2 as a monomial or as a subvert in a monomial?
No. It's not appears in M2. It appears
FM2.
It appears in yes. It appears as so F of M2 is a linear combination of monomials, and we require that one of those is M1. So yes, as one of the monomials, a linear combination.
So if M1 is a subvert, then it's not necessarily less than M2.
Yes, then it does not enter this definition. That's right. Yeah. Okay. So now let me. Once we have, once we talk about rewriting systems, you can somehow think that any rewriting system, you can think of any writing system as of a deformation of a trivial one. So somehow you have a trivial writing system that just rewrites some certain monomials to zero, which corresponds to extremely simple, extremely manageable algebra. So somehow, so each writing system which let me say each terminating rewriting system, because if a writing system is not terminating, we don't really have much to say in any case. Each terminating writing system can be viewed as a perturbation, let's say, of the trivial one, where each monomials are rewritten to zero. And somehow each convergent rewriting system can be leads to an algebra which can be viewed as a deformation of an algebra with monomial relations in a certain sense. So leads to an algebra that is a deformation in a certain sense of an algebra with monomial relations. relations. What does that mean? This means the following. So as you remember, for an algebra with monomial relations, the product of two basis elements is either a basis element or zero. When we have a convergent rewriting system, the multiplication table for basis, so first of all, for a convergent rewriting system, the basis of the algebra doesn't change. Because the condition of uniqueness of normal forms means that unwritable monomials in particular are linearly independent. So somehow we have the same basis of unwritable monomials, but the multiplication table changes. Namely, now each monomial, we don't write monomials to zero, but we write monomials into something which is smaller with respect to the partial order we discussed earlier. So monomials are written as linear combinations of smaller ones. And so the meaning of the word deformation is precisely that somehow we don't change the basis, but we change multiplication table by throwing in some lower terms. Okay, I'll just put the light on. Right. So now this is what I wanted to say about Grobner basis and rewriting systems. Now, in terms of so the second thing that I wanted to say.
I'm sorry. Just to make sure I understood. So you said that the system being terminating is equivalent to this being an Artinian partial order, or that's not quite true?
To it being an Artinian partial order. This is true, yes. Yeah.
And is there like for convergence, is there some kind of simple order theoretic condition we can
this is a great question. So somehow maybe I should say indeed that for convergence, so convergence is a more subtle thing in that so as you indeed remarked, termination is some kind of combinatorial property of this partial order. For convergence, it will be important, for example, what are the exact coefficients of the lower terms and so on. And the criterion of convergence is one of the criterions of convergence is given by that thing which is called the diamond lemma of Bergman. And in a few moments, I will remind you what this lemma states, but in any case, there is somehow a criterion which you can even sort of ask a computer to check for you. So there is a very explicit criterion of what you need to check for the purposes of convergence.
Okay, thanks.
Now, very briefly, to mention a few words about models of algebras. So, by the way, so how much time do I have? Because
well, we usually have something in between 1 hour and 1.5, so well,
okay, so
plenty of time.
Yeah. So that is amply sufficient. Thank you very much. Models of algebras. So somehow in the context of Grobner basis, the slogan is somehow that so the idea is to try to reduce studying difficult algebras to studying simple algebras with monomial relations, and then somehow cleverly throw in the lower terms. In the context of homotopical algebra, the approach is different. The approach is that if you have a complicated algebra, you can try to replace it by a much simpler differential graded algebra. So somehow the general idea, you can replace an algebra A by a free resolution, meaning it will be a tensor algebra, so something like this, where V is a graded vector space. Let's say non-negatively graded for the purpose of this talk. And D, which so it's a graded derivation of T of V, meaning the following, that grading of V leads to a grading on T of V by adding degrees. And you say that now D satisfies the graded Leibniz rule. D of AB is equal to D of AB plus minus 1 to the power degree of A D of B. Graded derivation of degree minus 1. So it reduces the total grading on T of V by 1 and satisfies D square equal to 0. And somehow, so the free resolution one means that, so since D square equal to 0, you can compute homology, and the homology of T of V with respect to this derivation in degree K, which again still corresponds to that grading that we have arising from the grading of V, is 0 for positive K and is isomorphic to A for in degree 0. So somehow the original algebra A was complicated. Now we replaced it by something which as an algebra is the tensor algebra, so it's a free algebra, but it has a priori a complicated differential. So that's another way to deal with with complicated algebras. And somehow, so in general, how to search for things like that? Well, if your algebra is presented by generators and relations, the logical thing is to say, so now suppose that A is k of x modulo r as before. Now we can start. As a first approximation, we define V0 as the vector space just linearly spanned by x. That's reasonable. We at least have, the tensor algebra of V0 is just the isomorphic to the free algebra generated by x. But our algebra A is a quotient. It's what to do. It's quite reasonable to say that now we say that V1, we take for V1 the vector space spanned by the relations, and we define a differential from a map from V1 to T of V0, which sends each relation. So let's call these basis elements ER, where R is a relation. And this map just sends every ER to the corresponding relation R in T of V0. Then, of course, if you define the part of the differential like this, at least the homology of degree 0 will be isomorphic to A. Because you forcefully imposed the relations. But of course, if you define this, then a priori you will have you won't have this remarkable condition that all the higher homology vanishes. So you need to do something else. You need to adjoin some things that will kill those homology cycles and so on. And so you can kind of construct a resolution in this way by killing cycles of higher and higher degrees. So somehow perhaps people tend to call this the Tate construction. In the 50s, Tate explained pretty much this in the case of commutative algebras, how to construct resolutions by gradually killing cycles. So in general, this procedure where you do just these two steps, where you starting from you replace A by this T of V0 plus V1 defined like this with this differential that creates the relations, this construction, so this incomplete resolution, has been studied in various contexts. People tend to call it the Shafarevich complex. It first appeared in a paper on of Gold and Shafarevich on the tower of in class field theory. So somehow, in any case, what I want to say is I am going to consider the only resolutions which are somehow extend this Shafarevich the Shafarevich complex. So below we shall discuss models which in some sense extend the Shafarevich complex. What do I mean by that? So now, at this point, let me remember that we are in the context of rewriting systems. So we have an algebra A, which we care about, where we have a rewriting system which we potentially want to be convergent, and we have the corresponding monomial algebra. we have the corresponding monomial algebra, which corresponds to this to the trivialized rewriting system where we just erase all the right-hand side. So this has a rewriting system, and this corresponds to the trivial rewriting system. So first of all, let me say that suppose that I have a model for this monomial algebra with several properties. Model such that first of all, I want it in addition to be graded in some sense by monomials. So the monomial algebra A mon is just the direct sum of all possible unrewritable monomials. And I want this T of V to be the direct sum of components corresponding to monomials in the free monoid, such that this makes it an algebra grading. So the product from TW1 and TW2 lands in TW1, W2. So I want the differential to respect this grading. So in our big algebra is decomposed as a direct sum of chain complexes corresponding to words. And in addition, I want in degrees 0 and 1, I want this model to look like the Shafevich complex. So somehow, now let me state the first result. So for now, if I only think about the monomial algebra, there is no, I don't yet have a rewriting system. I don't care about the order. The order starts to matter once we incorporate the lower terms. This is just a very combinatorial situation where we just have everything is we have this additional grading by words, but there are no order is involved. Now we go back to A, and the first result is that convergent writing systems correspond to perturbations of models.
Excuse me.
Yeah.
So in this, just in the this definition of this model corresponding to a rewriting, is this like a complete definition? Because I'm not quite. So there's
no. So this here, it is not a definition. I suggest to fix some model of the algebra with monomial relations, which has this addition fine grading by monomials. There are many choices, and in the end of the talk, I mentioned at least 2 different interesting choices. But for now, choose one particular model with these properties. Okay?
So just in number 2, the relationship with the Shafarevich complex, it is not obvious what the so in degree 1 what the gradings by the free monoid should be. That's not obvious, right? Right?
The point is that elements for the Shafarevich complex, V0 is just spanned by letters in the alphabet X. V1 corresponds
to relations, and they're not homogeneous.
Yes, correspond to relations which in our case are monomials, because it's the Shafarevich complex
so they're
for
homogeneous.
the A mon. Yeah.
Okay, thanks.
Your question is very good, but in this case there is absolutely no problem because everything is graded.
I just missed that part. Okay, thanks.
Yeah. No, I should have been specific that. Yeah. So what I mean is the following. A rewriting system sigma is convergent if and only if there exists a perturbation d prime of the differential such that T of V with D plus D prime is in degrees 0 and 1 looks like the Shafarevich complex of A. Then for each the homology of T of V D plus D prime vanishes in positive degrees. And finally, the third thing is that for each element X in T of V or of certain word degree W, D prime of X is a combination of elements which are in of word degrees less than W with respect to the partial order associated to our writing system. W prime less W T of V W prime. So this is the partial order associated with the writing system discussed before. So the system is already assumed terminating. So somehow, but this is a fancy way to give a criterion of convergence. So this result is relatively easy to prove. Somehow it's there are some standard techniques of homological perturbation that are designed to prove exactly things like that. So instead of talking about how this theorem is proved, I'll tell you how this theorem can be used to recast this condition in terms of the so-called tangent complex of our algebra. So
I'm sorry
yeah.
about the theorem. So just this model T of VD, which is in the theorem, this is any model with the above properties, or
yes, that's correct. So so somehow each model of the corresponding monomial algebra gives you some criterion of writing of convergence for a writing system. Yes.
And the fact that at least such one model exists is obvious, or
well, so I suppose that if you just apply the Tate process of killing cycles and make sure that you keep everything homogeneous, then you will arrive at such model. That's a quick answer, but I will give you a slightly better answer, hopefully towards the end. So, but a priori, it is more or less obvious that such models exist. Yeah.
okay, thanks.
Right. So somehow, so to talk about the tangent complexes. So a tangent complex of an algebra associated to a model is just the graded Lie algebra of derivations of a model. So somehow a tangent, well, a tangent complex of an associative algebra is the Lie algebra of derivations of a model of that algebra. So you see that it certainly depends on the choice of a model, but it is possible to show that in the homotopy category of Lie algebras, actually it is something well defined. So somehow the tangent complexes, they differ from each other only up there is the only difference is to replace it by something homotopy equivalent. So actually I should say here differential graded Lie algebra. So to be precise, so a model, so we have an algebra A, we have its model T of V equipped with D, and so somehow let me say B, and now the tangent complex TA as T associated to this model is just the Lie algebra, the graded Lie algebra of derivations of the model, equipped with the differential D, which is just the bracket with the differential of the model. So the differential of the model is an example of a derivation, and somehow the because it squares to 0, it's easy to show that taking the commutator twice vanishes, so it actually defines a differential on the graded Lie algebra of derivations. Now, what I want to say is the following: that in differential graded Lie algebras, one usually considers what is called the Maurer-Cartan equation. Which says that so the differential graded algebra L with so the Maurer-Cartan equation dA plus 1/2 bracket of AA is equal to 0 for elements A of degree -1. So somehow again, we're talking about graded Lie algebras, so it's antisymmetric. The antisymmetry takes into account the homological degrees. Xy is equal to minus 1 to the degree x, degree y, yx, and all exchanges of things involve this Cajal sign rule that takes into account degrees. So in particular, the bracket of element of degree -1 with itself is a priori non-trivial, and this equation is what is called the Maurer-Cartan equation, and which you even if you don't care too much about differential graded Lie algebras, you probably would have encountered in differential geometry in the context of equation for flat connections. But what is important here is that in the case like the one we have, where D is the bracket with something where the differential is internal, the Maurer-Cartan equation can be rewritten as D plus A bracket with D plus A is equal to 0. So somehow, and this means that A is a perturbation of the differential D. So the solutions to the Maurer-Cartan equation in the tangent complex are just perturbation of the differential. That's something which is important to have in mind. Now, let me state the next result. So suppose that we have a model as above, model of the monomial algebra. So with additional grading by monomials. Now a writing system sigma is convergent if and only if there exists a degree -1 element F in the Lie algebra of derivations, such that first of all, for each ER inside V1, so I remind you that we are extending the Shafirevich complex, so V1 is spanned by elements ER. F of ER.
So Volodya, I'm sorry, in particular, R is a monomial, right?
Yes. So perhaps to emphasize it, let me call it W to emphasize that it is a monomial. F of EW is equal to minus F of W, so it's the more or less the lower term of the rewriting system. That's one condition. The second condition is that F, when restricted to V2, is compatible with our filtration. So meaning that that somehow the image of each element of certain word degree is a combination of elements of smaller degrees with respect to with filtration given by this ordering with respect to sigma. And the third thing is that the Maurer-Khaitan equation df plus 1/2 the bracket of f with f is equal to 0 is not necessarily fully satisfied, but it holds when so this element so holds up to degree 2. I will explain immediately what this means. So df plus 1/2 of bracket of f with f, which is an element of the which is a derivation of the model. So this element vanishes when evaluated on vanishes on V0 plus V1 plus V2. And this is already so this is already quite enjoyable for the following reason. So if you forget about the last condition, then this well, sorry, but if you require the last condition, globally, you require that the Maurer-Khaitan equation just holds a full stop. Then it is just a reformulation of the previous results, because somehow I said that solutions to Maurer-Khaitan equation are perturbations of the differential, so we just go back to the theorem talking about perturbation of differential. But this is very good because somehow there is this extra bit saying that we need to verify things just up to order 2, that in higher homological degrees, even if something doesn't work, we can tweak it a little bit so that Maurer-Khaitan equation will be satisfied. So somehow this is already, it requires some proof, but well, it works. And so this is very useful. So somehow, yeah.
So is it true that the existence of such an F is equivalent to the existence of an F for which it vanishes in all degrees?
Yes, exactly. So this is the non-trivial part of the theorem. Exactly. So somehow, so vanishing to all degrees, it's the previous theorem, and the non-trivial part here is that up to degree 2 is sufficient.
But it may be a different F.
Yeah. So in principle, it might happen that you start with F, which works up to degree 2, and then in degree 3 there is a little bit of problem, and then you change that little that F in higher degrees so that everything starts working. Exactly. Yeah. Right. Now I will explain to you. Do I have perhaps 10 more minutes?
Sure.
Yes. So let me now explain to you why this theorem, which talks about solutions to Maurer-Khaitan equation, actually is close to Bergman's diamond lemma, for which I need to tell you what the Bergman's diamond lemma is. And let me tell you very, very quickly. So the diamond lemma of which is Bergman 76 works as follows. It says that so remember in the beginning, I gave you that example of the rewriting system, xy goes to 1 and yz goes to 1, and they rewrite into two different things. So diamond lemma says that things like that are sort of the only problems to convergence that could possibly occur. So diamond lemma says that a rewriting system is convergent if and only if all diamonds close up in the following sense. So suppose that you have a word W that can be rewritten in two different ways. So there is one rewriting rule to, so this is, well, I don't want to insist that it's the right-hand side of a rewriting rule. You have a monomial M that is divisible perhaps inside by W1 and W2, and so it can be written in two different ways. So according to, there is one rewriting rule F1 and another rewriting rule F2 that rewrites it into a combination of monomials. So somehow the diamond condition says that you must have some sequences of rewriting rules applicable to the results here that arrive in the exact same place. This is what I mean by the diamond clauses. So that a priori you can rewrite an element in two different ways, and then you go and you see that you need to be able to show that those things can be written further so that they arrive in the same place. Important thing is that inside the monomial M, what can happen? W1 and W2 can be just parallel, can be independent inside M. In this case, such diamond always closes. That's very easy to show. So this does not impose any conditions. In fact, that's very easy. There are two other situations. You can have some non-trivial overlap of W1 and W2 inside M. Or you can have a situation like this, W1, for example, W2, one of them is a subword of another. And somehow, so what happens outside is not really relevant. You can again show that it does not affect the fact that diamond can close or not. And so combinatorially, what you need to check for convergence, this is going back to the question that asked earlier. What you need to you look at your writing rules, you look at how they can overlap or how they are how the left-hand sides can overlap or be included in one another. And for each such situation, do the corresponding diamond and see if you can close it up or not. And this gives you a criterion for convergence. Now, let me try to explain to you very quickly how to think about this condition in the context that I have been talking about. For that, let me address another question that was asked, and let me give you an explicit example of a model for the monomial algebra, for each monomial algebra. So suppose that I have now, so I have my X, I have R, which is a set of monomials. Let me define a model. So as a vector space, the model, what I'm going to call inclusion-exclusion model, is spanned by expressions of the form M tensor S1 wedge S2 wedge SP, where M is an element is a monomial, possibly divisible by some relations, so no restrictions. And these letters, these S1, S2, SP, they indicate different, they correspond to some subwords of M, which are relations. Some subwords of M that are relations. And of course, things like that you can multiply. You can, if you M tensor S1 wedge SP multiplied by M prime S1 prime SQ prime, you write it basically as the concatenation of M and M prime and the wedge product of S1 SP, and perhaps I should write S1 prime with tilde S. Well, maybe let me put tildes everywhere, but what I mean to say is that in this concatenation M prime, there are some relations which were divisors of M, and they correspond to these letters S1 tilde, SP tilde, and inside M prime there are the corresponding things, the divisors which were corresponding to these, and they, so it's just that I want you to remember that these letters S, they really remember the place where a divisor occurs. So in particular, they are all, this set of letters and this set of letters have zero intersection because these correspond to something that occur inside M, and these correspond to something that occur inside M prime.
Okay, I'm sorry, I'm a bit confused. So in your, so you have P relations, yes, W1, WP, and then
yeah,
P's, and then in the fourth line.
Yes, well, let's,
okay.
yeah, I'm sorry. This P has absolutely nothing to do with that.
So it means that each of SI takes its own W and then finds some piece there.
No, it is just a little bit different in that two different SIs might correspond to the same W, but different place in which this W occurs. So for example, suppose that R is equal to X squared, right? And let's consider M equal to X cubed.
Okay.
Then in x cubed, you have the left divisor x squared and the right divisor x squared. And so a priori, you have elements m tensor 1, no letters, we don't care about any of these divisors, m tensor s1, so we care about the left divisor, m tensor s2, we care about the right divisor, and m tensor s1 wedge s2, where we care to remember both of these divisors.
Okay. Okay, I see.
Right. Now, so you have the concatenation product, and you have the differential, which is just the differential of m s1 wedge sp is equal to the sum minus 1 to the power I minus 1 m tensor s1 wedge si omitted sp. So it's really sort of the inclusion-exclusion differential, if you want. So you look at the set of all divisors of all divisors of m, which are relations, and yeah. So this more. So what I claim is that I'm sorry. I claim two things. One is that the underlying algebra is free. And is actually freely generated by indecomposables, which are the things which are not obtained like this. So somehow, yeah. So which are monomials that you cannot represent as a product. So some of the letters S correspond to the left part, and some correspond to the right part. Then the homology of this algebra is just H0, which is isomorphic to our algebra with monomial relations. All the higher homology vanishes. And this is this more or less follows from contractibility of simplices. So that's why it's called the inclusion-exclusion model. And of course, this is graded by the free monoid because the differential doesn't change m, the product just concatenates the words. So it's remembering just the monomial gives you a grading. And now the final claim is that the criterion, the Maurer-Cartan criterion applied to this model is precisely the diamond lemma. So the Maurer-Cartan criterion, it's that existence of a derivation which satisfies the Maurer-Cartan equation in degrees at most 2. So in fact, in degrees 0 and 1, the Maurer-Cartan equation is trivial. Everything vanishes for degree reasons. So the only thing to check is the order 2 thing. And the order 2 thing, what does it mean? The order 2, you need to look at indecomposables of your algebra of degree 2. So things of the form M tensor S1, S2, where S1 and S2 point at some divisors which are relations. Since M is indecomposable, these two relations either form an overlap or one included into another. Otherwise, everything falls apart. It's not an indecomposable element. And if you write the Maurer-Cartan condition, if you write the Maurer-Cartan condition, you will see precisely that existence of that F well, sorry, not the existence or the compatibility of F with filtration is precisely closure of all diamonds. So conditions that you check correspond to overlaps and inclusions. And if you write the Maurer-Cartan equation and see what this means, remembering that F is compatible with filtration, this really shows that all that for every picture like that, the corresponding diamond has to close up. So somehow thinking about the diamond lemma is thinking about this combinatorial resolution of this particular combinatorial resolution of an algebra with monomial relations. This resolution is not minimal. For algebras with monomial relations, it is possible to describe minimal resolutions quite explicitly. This was actually done by Pedro Tamayev some years ago. And it turns out that if you apply the Maurer-Cartan criterion to the minimal resolution, you will obtain what the improvement of the diamond lemma, which is called the triangle lemma, which explains precisely what overlaps are do contribute non-trivial conditions in checking if a writing system is convergent. So this is in any case a kind of big picture overview, but with certain details. I think that I already have taken an awful lot of your time, so it's best to stop here, and thank you for your patience and for your questions.
Спасибо. Поскольку Giovanni отключился, то можно по-русски.
Хорошо.
Какие-нибудь вопросы?
А вот это последнее клейм, это как бы метод доказательства теоремы, да, которая там.
Это от утверждения, что предыдущая общая теорема имеет своим последствием бриллиантовую лемму Бергмана, если рассмотреть данную конкретную резольвенту.
Ну то есть доказывается она не так. Доказывали вы ее...
Нет. Сама теорема, которая говорит, что достаточно все проверять до степени 2, это, как это называется, по-английски я бы сказал basic abstraction theory, то, что мы хотим все проверить, что это вплоть до степени 2 позволяет построить что-то, что работает во всех степенях. И мы это просто бережно смотрим степень за степенью, и из того, что мы стартовали с резольвента, из ацикличности, просто довольно легко следует, что можно все подправить так, чтобы все улучшилось.
Я, наверное, запутался. А почему нельзя доказывать через вот это утверждение? То есть вы говорите, что Значит, ну, вот эта лемма бриллиантовая дает критерий для, как сходимость, да, по-русски, convergence.
Наверное, да.
И вот вы, значит, а вы говорите, что вот это утверждение о степенях 1 и 2, 0, 1 и 2, оно равносильно вот бриллиантовой лемме. То есть это...
Оно равносильно бриллиантовой лемме для конкретного выбора резольвента. Каждая резольвента дает свой вариант бриллиантовой леммы.
Ну хорошо, то есть как бы это только частный случай теорем можно доказать таким образом.
Да.
Угу. У меня на самом деле был про бриллиантовую лемму еще вопрос, я просто пытаюсь понять ее нетривиальность. То есть так на первый взгляд кажется, ну то есть это чисто такое теоретико-графовое утверждение, да, то есть мы можем такой взять граф, у которого вершина там все элементы нашего кольца, вот эти ребра это вот эти переходы, и как бы сходимость это там то, что, не знаю, в каждой компоненте связанности есть один, как называется, сток, да?
Да.
Ну и то есть это просто утверждение, что как бы у каждых двух вершин должен быть такой мид, да, то есть, ну это такое, бриллиантовая лемма это простое теоретико-графовое утверждение или нет?
Значит, тут есть такое дело, что во-первых, общий ответ да, конечно. И в частности, Бергман свою статью начинает словами, что это статья о тривиальном утверждении. В каком-то смысле, то, о чем я говорю, это вещь такая вдвойне тривиальная, что это некоторое такое гомотопически, что ли, тривиальное доказательство тривиального утверждения. Да. Но дело в том, что при всей своей тривиальности это оказывается невероятно удобно. Ну, например, я сфокусировался в докладе на ассоциативных, не обязательно коммутативных алгебрах. Для коммутативных алгебр ситуация, например, оказывается приятна тем, что это все алгоритмично в очень строгом смысле, что всегда для любой коммутативной алгебры существует конечная сходящаяся, это переписывающая система, что не нужно организовывать бесконечное количество rewriting rules для того, чтобы все работало, что в принципе априори не совсем очевидно, да? Потому что, например, когда вы говорите про граф, вы хотите рассматривать граф, у которого вершины это элементы алгебры, может быть даже линейные комбинации, то есть
я хотел сказать, что в гребневском случае это очевидно, но так вообще нет.
Ну, нет, в данном случае при том, что это утверждение действительно несложное и в какой-то степени может быть очевидное, оно позволяет доказывать вещи априори не вполне тривиальные. И я должен сказать, что огромное количество вещей, которые мне в моей математической деятельности удалось доказать, зачастую мне удалось доказать потому, что я, может быть, лучше понимал, чем какие-то другие люди, разные способы, которыми бриллиантовую лемму можно применить для того, чтобы нечто сделать. И с другой стороны, в течение очень долгого времени я про про бриллиантовую лемму думал как про некоторую комбинаторику, которая существует как бы отдельно от всего. И мне, как большому любителю грамматофической алгебры, искренне приятно, что она имеет такого рода объяснение, что что нету такого исключения. Мы знаем в соответствии с давними заветами Дейнфельда и прочих, которые претворены в жизнь Джейкобом Лури и прочими, что задачи теории деформаций описываются изучением решений уравнения Мауэр-Хартана в дифференциальных градуированных алгебрах Ли. И задачи, бриллиантовая лемма, про нее естественно думать как про такой тривиальный пример из теории деформации. И поэтому мне лично очень приятно, что она может быть проинтерпретирована таким способом.
Хорошо, спасибо.
Можно еще раз фактически повторить? На самом деле вы как бы ответили на вопрос, но все-таки еще раз задам, может быть, тривиальный вопрос. То есть вот то, что вы пытались объяснить, это вот некое объяснение такого вот, может быть, известного факта о деформации структур ассоциативной алгебры и о существовании единственности такой деформации. Это равенство нулю там, первых, вторых когомологий там, Хохшильда. Вот то, что вы объясняли, это не уточнение, не знаю, обобщение или объяснение в терминах бриллиантовой леммы вот этого факта, да? Правильно ли это думать?
Про это связанные вещи. То есть, безусловно, комплекс Хохшильда для ассоциативной алгебры – это один из способов построить касательный комплекс и изучать теорию деформации.
Да, совершенно верно, да.
Для целей, для того, чтобы говорить про бриллиантовую лемму, комплекс Хохшильда является не вполне удачным игровым полем, потому что он в каком-то смысле слишком маленький. Концепты Хохшильда принимают значение в самой алгебре, в то время как критерий бриллиантовой леммы – это некоторое вычисление внутри свободной алгебры. Поэтому для этих целей желательно другая модель для касательного комплекса, возникающая как дифференцирование резольвента. В каком-то смысле вот это условие про выполнение вплоть до степени 2, я бы сказал, что это иллюстрация скорее иллюстрация известного принципа Гельфанда, что когомологии ведут себя как производные, что есть скорость, ускорение, а дальнейшее физического смысла не имеет. Вот. В этом смысле то, что вплоть до степени 2 важно и что-то контролирует, а все высшее можно немного подкрутить, чтобы все стало работать.
Ну, хорошо, да. То есть это как бы скорее некий аналог, да, то есть это не прямое обобщение.
Это вещь в некотором смысле параллельная, я бы сказал.
Да, ну вот, собственно, в этом вопрос.
Что вы правы, что изучать уравнение Мауэр-Картана в комплексе Хохшильда, безусловно, вещь вполне осмысленная для некоторых задач теории деформаций. Если мы хотим включить бриллиантовую лемму в контекст теории деформации, то мораль состоит в том, что полезно использовать другие инкарнации касательного комплекса, которые более похожи в которых больше играют роль какие-то свободные алгебры, ассоциированные с нашей, то есть свободные изоленты.
Спасибо, да, более-менее. Понятно, спасибо.
Еще какие-нибудь вопросы?
Можно тогда я еще один вопрос задам, так может немножко в сторону про вот эти rewriting system, не знаю, как системой переписывания.
Наверное, я никогда
да, как по-русски правильно переводить?
Ну, в общем, да. Ну, то есть, давайте даже вот, может, сосредоточимся на коммутативном случае, да?
Да.
Вот у нас, давайте зафиксируем, вот у нас есть, значит, коммутативное кольцо многочленов, в нем идеал, да? То есть вот у нас задана алгебра с отношениями и порождающими. И вот мы, кроме того, зафиксировали вот это, ну, не знаю, ОМОН, ну, вот это вот вырождение, которое получается. То есть мы рассматриваем все системы, которые для этой системы соотношений дают вот такую вот мономиальную алгебру.
Да.
Ну вот, например, если вот в рамках грёбнеровского сеттинга действовать, то там их конечное число, да, а вот таких конечное число... Нет, я неправильно сказал. Извините, давайте мы зафиксировали алгебру и систему соотношений. Верно ли, что из нее, вот можно рассмотреть все rewriting systems для нее, каждая из них дает какой-то мономиальный идеал, да, который порождается вот верно ли, что этих мономиальных идеалов будет конечное число? То есть можно конечное число разных вырождений получить таким образом, или их уже бесконечно много можно?
Вы имеете в виду, Игорь, что типа аналог какого-то этого веера Грёбнера, да?
Ну нет, до веера тут еще далеко.
Ну, значит, там конечное число этих самых конусов максимальный размер.
Ну, как бы да, ну такое базовое утверждение, что как бы у каждого идеала есть конечное число начальных идеалов. А вот верно ли про эти rewriting systems какой-то аналог этого утверждения, или это уже гораздо более такая сложная вещь?
Это хороший вопрос. Я про него никогда не думал. Да, сходу я ничего сказать не готов. То есть на самом деле очень вероятно, что этим вопросом, может быть, просто никто и не задавался никогда, потому что тут такое дело, что в каком-то смысле в некоммутативном случае эти переписывающие системы, let's say, их в каком-то смысле используют от некоторой безысходности, потому что не так много полезных, хороших, полных порядков на некоммутативных мономах. В коммутативном случае жизнь немного проще или даже сильно проще, потому что все порядки более-менее классифицированы, да, они соответствуют некоторому набору весов. В некоммутативном случае, кажется, был когда-то так, может быть верно, что для моноида с двумя образующими все порядки классифицированы, но дальше уж точно ничего не известно, и поэтому зачастую приходится использовать частичные порядки, чтобы чего-то добиться. На частичные порядки в коммутативном случае, я думаю, что очень мало кто смотрел, поэтому этот вопрос, да, вопрос естественный, ответ может быть неизвестен.
Ну, то есть мы берем набор порождающих, и из каждой, по сути, просто из каждой выбираем по одному моному, и вопрос, ну, то есть мы берем бесконечный набор порождающих, да, не очевидный вопрос, не очевидный, согласен. Ладно, спасибо.
Нет, то есть я думаю, что с другой стороны, может быть, не, окей, let's forget it. Я собирался сказать, что что-то заведомо недостаточное, так что лучше не надо.
Еще какие-нибудь вопросы? Если нет, то, Володя, большое спасибо.
Да, я еще раз прошу прощения за незнакомство с системами часовых поясов.
Спасибо.
Ну, это ничего, слава богу. разрешилось быстро.
Да.
Мы уже думали, может, вам позвонить.